R5, rational expressions. So rational expressions are kind of like rational numbers. If you remember rational numbers, you needed to have two integers that were being divided, one into the other. So P over Q, some integer divided by another integer. Well, a rational expression is the quotient of two polynomials. So capital P over Q. So it's rational functions, you could say. So P divided by Q, and obviously Q cannot be equal to 0. Okay? So if we're looking at a rational expression, which is just a polynomial divided by another polynomial, we cannot allow that polynomial in the denominator to be equal to 0. Therefore, there's going to be a restriction on our domain of this rational function that Q cannot be equal to 0. Otherwise, we assume that the domain is all real numbers. So we allow the domain to be all real numbers except for those real numbers that will cause Q to be equal to 0. Now, if we're trying to find those values that will make Q equal to 0, we need to remember the zero factor property. Right? Zero factor property says that if you take A times B and it's equal to 0, that can occur if A is equal to 0 or if B is equal to 0. Because anytime you multiply a number by 0, you get 0. So when we're dealing with a rational function, this rational expression, then we can factor Q, and for each of those factors, we find when it's equal to 0, and that's going to create our domain, or it's going to determine what will not be part of our domain. So let's take a look at some different examples of this. We'll start with something really easy, and then we'll move into something just a little more complicated. So what if we have x plus 5 over x minus 2? That is a rational expression. We have x plus 5, which is a polynomial, divided by x minus 2, which is also a polynomial. But we know that x minus 2 can't be allowed to be equal to 0, otherwise we're dividing by 0, which again makes it undefined. So we can't allow that, so we just need to know when will x minus 2 be equal to 0. And I know you're screaming at me while looking at the screen saying, Mr. Davis, it can't be allowed that x is 2. Because if x is equal to 2, then we're going to have 2 minus 2, we're going to have 0. So obviously, yes, x cannot be allowed to be equal to 2 because that would make the denominator 0. So therefore, the domain of this rational expression is all real numbers such that x is not equal to 2. Well, what about this numerator? Does that have any effect? No, it doesn't really. Not on the domain, because I can allow x to be equal to any real number for the numerator. If I make it negative 5, yes, the numerator becomes 0, but it's okay to take 0 and divide it by things. 0 divided by any number is just going to be 0. You just can't divide by 0. So we have to look at the denominator and make sure it's not allowed to be equal to 0. Well, let's try another one. X minus 7 times x plus 3 over x plus 1 times x plus 4. And we want to find the domain of this rational expression. Well, looking at this rational expression, remember, all that matters for the domain is what's going to cause this denominator to be equal to 0. Well, we have x plus 1 multiplied by x plus 5. So if x plus 1 is equal to 0, then our denominator is going to be 0 because of the zero factor property. Or if x plus 4 is equal to 0, then the denominator is going to be 0. So therefore, if x is equal to negative 1, or if x is equal to negative 4, so if x is equal to negative 4, either of those cases will turn that denominator into 0, which will make this undefined. So all we have to say is the domain is all real numbers such that x is not equal to negative 4 or negative 1. So that's how we find the domain of a rational expression. So nothing too complicated. It's just a matter of being able to factor the denominator and check each factor and say, okay, when is it going to be equal to 0? And we can't allow that to happen. Well, okay, so that moves us forward. Well, what we can also deal with rational expressions is, remember I said rational expressions kind of like rational numbers, right? A divided by B, an integer divided by another integer. Well, what is a rational number? It's really a fraction, right? An integer divided by another integer, that's just a fraction, a ratio. So the same thing with rational expressions, it's just a fraction or a ratio of two polynomials. Well, what do you do with a fraction anytime you're working with it? You simplify it, right? Simplify or reduce the fraction. Once you're done with everything else, simplify or reduce. Same thing with rational expressions. We need to be able to simplify or reduce the rational expression. When is it simplified? When we remove all the common factors between the numerator and the denominator. So what if we have x minus 1 times x plus 7 times x plus 2 over x plus 7 times x plus 5 times x minus 1. So we have a rational expression, and yes, I know I'm kind of making this simpler on us because I'm not actually writing these out as polynomials, I'm writing them all already factored. But we should already know how to factor polynomials. We covered that previously. So if you need to refresh that, go and do that. But basically all we're looking for here is, okay, well, if we have any common factors in the numerator and in the denominator, let's get rid of them. I'm going to change to a different color just so it's obvious what's going on here. So I look and I've got x minus 1 in the numerator. I have x minus 1 in the denominator. So there we go, we cancel them out. I've got x plus 7 in the numerator, x plus 7 in the denominator. Cancel them out. I've got x plus 2 in the numerator. I do not have x plus 2 in the denominator. So I guess what we're left with is x plus 2 over x plus 5. Now, something I want to point out about this, though, is that what if we're asked the question, what is the domain of this rational function or this rational expression? Now, if we look at this, the result, our simplified rational expression, and we say x can't be equal to negative 5. Right? Because if x is equal to negative 5, then we end up dividing by 0. But we have to be careful because we did start with this function. So we cannot allow this function to divide by 0. So the domain of this function is really x not equal to negative 7, negative 5, and 1. So we can't allow the original expression to be equal to 0. So therefore, we should find the domain first and then simplify. Now you may ask, but why? If it simplifies to this, what do these matter? And that's an excellent question. Now, what that gets into is this expression, the expression came from somewhere. This polynomial in the numerator and the polynomial in the denominator came from somewhere. Be that electrical circuitry or mechanical forces or something else, chemical reactions, whatever the case may be. This came from somewhere. In reality, this came from my head. But in the real world, this came from somewhere. And yes, you have this here which cancels out that there. We have this here which cancels out that there. And that's fine for how we look at the result and what happens. But it's not fine in the sense that these things were actually in the circuitry or in the mechanical system or in that chemical reaction. So we can't ignore the fact that they were there to begin with. They still exist. It's just these two things are working against each other. Looking at the electrical side of things, if you're familiar with that, just think of the effect of capacitors and inductors. They have a tendency, and you'll actually see this when you get into, well, I guess you won't see it in that. When you get into different electrical courses, if you go into, you'll see that there is a phase shift that happens depending on whether you've got a capacitor in a circuit or an inductor in the circuit. And what you can do is you can adjust for the phase shift caused by a capacitor by putting an inductor in there. So you can compensate for it so that you get the energy going out that you hope for. But you can't ignore the fact that there's a capacitor in there and there's an inductor in there. They're still doing what they do. They're just canceling out a certain effect in the end. And that's what happens here. They're canceling out a certain effect in the end, but we cannot ignore their existence. It'd be great if we could, but we can't. Now, for those of you who are complaining that I already started with these factors, so what happens if we're actually given a polynomial? Well, let's look at the following. 2x squared minus 6x over, let's go 5x squared minus 14x minus 3. Okay? So we have this. And I say, okay, well, let's cancel or simplify and find the domain. Remember, you should actually do the opposite. Find the domain and then cancel and simplify. So I'm just going to switch to a different color here. So let's start with the numerator and factor it. Remember, whenever you're factoring, you always go for the greatest common factor first. So I see 2x squared minus 6x. I see that I can pull a 2 and an x out of that. So I'm going to come over here, I'm going to make that 2x, and that leaves me with x minus 3. Okay, that was the really easy one. So now let's look at this one. Well, I do not see any common factors that I can pull out of this. 5, 14, 3. This has an x squared and an x, doesn't have an x. So I can't do anything there. So let's factor by grouping. So 3 times negative 5, 5 times negative 3, state the correct things, gives us negative 15. So we want two numbers that multiply to negative 15 and add to negative 14. Well, that should be pretty straightforward. 1 times negative 15 gives you negative 15. 1 plus negative 15 gives you negative 14. So we've got 1 and negative 15. So we can break this up into 5x squared minus 15x plus 1 minus 3. You remember we just split this up into those two pieces. Don't forget the x there. Okay? So now I can factor by grouping. I'm going to get this out of the way just to give me space. Now why did I choose to put 15x here instead of the 1x here? Well, I saw 5 and I saw 15 and I figured, well, that's going to allow me to pull something out. Remember, it doesn't matter if I put plus 1x minus 15x, we still would be able to do it, we'll come out with the same result. So I look at these first two and I can pull out 5x, leaving me with x minus 3. I look at these and I just see a 1 in common, so plus 1. And don't forget to pull out that 1. It's a common mistake for people to go, oh, there's nothing in common, and they just go plus and they put their x minus 3 in it. You need that 1. So you're always going to pull out a common factor, even if it's just 1. Leaving us with x minus 3. Therefore, we have a common factor of x minus 3, and that leaves us with 5x plus 1. Okay, so we have x minus 3, 5x plus 1. So now we can find the domain. So the domain, we want to make sure the denominator is not equal to 0. So if x minus 3 is equal to 0, that happens when x is equal to 3, and 5x plus 1 equal to 0. So when 5x is equal to negative 1, or x is equal to negative 1/5. So our domain will be x not equal to negative 1/5, 3. So we can't allow either of one of those to be in there. And now we can simplify and go, well, I've got an x minus 3 and an x minus 3. We get rid of those. I'm just going to put a big D here as a domain so we remember what that is. That's just our domain. Remember, we assume all real numbers except for what's going to cause the denominator to be equal to 0. Leaves us with 2x over 5x plus 1. And we have simplified that rational expression. So just factor it. Determine what values will make your denominator equal to 0, and that's going to be your domain. You're not allowed to have it equal to those values. And then cancel out any in common. So there we go. So that's simplifying. Well, let's go into some other things that we can do with these rational expressions. Okay, so in addition to what we've done, we can now get into addition, subtraction, multiplication, and division of rational expressions. Now, if you remember with fractions, multiplication and division are actually easier than addition and subtraction. Why is that? Because multiplication and division do not require a common denominator. So we're going to start with multiplication and division, and basically what we're going to say is if you have two rational expressions, a over b and c over d, where b and d are not equal to 0, remember you've got to put that requirement in there, then we can say that A over B times C over D is equal to AC over BD. Still, B and D cannot be equal to 0, right? But that's just what you learned with fractions. If you want to multiply fractions, multiply the numerators and multiply the denominators. Please do not say cross multiply. This is not the correct spot for cross multiplication. Cross multiplication would be multiplying like that. Okay, so do not say that. This is just multiplying across. So that's how we can multiply rational expressions. If we have x plus 3 over x minus 2 times x minus 1, let's make that a full parenthesis, over x plus 7, then that multiplication just gives us x plus 3 times x minus 1 over x minus 2 times x plus 7. And yes, if we were dealing with this and solving it, or actually doing the multiplication, we would then want to FOIL the numerator and FOIL the denominator after we've simplified. And there's nothing we can simplify here, so we would multiply that through and get x squared plus 2x minus 3 and x squared plus 5x minus 14. So we would do that if we were going that far, but we're just showing how the multiplication works. Well, what about division? What do you remember about division of fractions? Well, division of fractions, how did we do that? We did that with multiplication, right? Keep it, change it, flip it. I like to teach people, keep it, change it, flip it, pop it. Right? You keep the first fraction as it is, change the division to multiplication, flip the second fraction, or take the reciprocal of it, and then solve it. Keep it, change it, flip it, and then I like bop it because bop is kind of cool. So keep it, change it, flip it, bop it. Or keep it, change it, flip it, solve it. Whichever way you want to look at it. So if we have A over B and C over D, where B and D are not equal to 0, then A over B divided by C over D is equal to A times D over B times C, as long as C is also not equal to 0. Right? Because now that we're going to put C into the denominator to change it to multiplication, that can't be allowed to be equal to 0 either. So we now, in this situation, when you're dividing rational expressions, you actually have 3 out of 4 parts that can't be allowed to be equal to 0, because the originally you had these 2 rational expressions which you couldn't allow either one to have a denominator that was equal to 0. But then to do the multiplication, you end up flipping the one, so its numerator can't be equal to 0 either. So if we have x minus 3 over x plus 5, guess I don't need to put that parenthesis in there, divided by x minus 3 over x plus 2, then we know that, for the domain at least, we know that x plus 5 can't be allowed to be equal to 0, x plus 2 can't be allowed to be equal to 0, and we can't allow x minus 3 to be equal to 0 in this case for when we get done multiplying. So that's going to mean that we can't have x equal to -5, -2, or +3. But when we do this, we're going to keep it, change it, flip it, and then simplify if we can. So what happens here? Well, we have x minus 3 over x plus 5. That remains the same. We change the division to multiplication. I'll just use a parenthesis. I find it easier when we're dealing with rational expressions. And then we flip it, so we have x plus 2 over x minus 3. So now we can multiply across. Well, remember when you're multiplying across that now we know we're going to multiply this times this and that times that. So we can cancel out now if we see anything that allows us to. And I do. I see that I'm going to have x minus 3 in the numerator and the denominator, leaving me with x plus 2 over x plus 5. But remember our domain, we can't allow x to be equal to -5, -2, or 3. So that's the biggest thing to pay attention to, I think, when you're dividing rational expressions, is realize there are actually 3 different parts of it that you cannot allow to be equal to 0. This is the only one that you can. This can be 0. But the other 3 can't, because somewhere along the way, they have to be in a denominator, which makes it a divide by 0 if it is. So we can't allow that to happen. So again, multiplication, division, that's the easy part. I should put easy in quotes. That's the easy part. Well, what makes addition and subtraction more complicated than multiplication and division? Just the fact that you need a common denominator. And I guess I could have left that up there, so imagine that we still have a over b and c over d, where both b and d are not equal to 0. So we're still working under that same framework. But when we get to addition, so we have a over b plus c over d. Well, what do we need to do? We need a common denominator. Well, in this case, when you're just using variables for it, that means that we're going to multiply those 2 denominators together. So it's going to give us something over BD. But what's going to happen? Well, that means that A is going to get multiplied by D, so you're going to get AD. And C is going to get multiplied by B plus BC. So AD plus BC over BD. Now remember, this is basing it on the fact that we don't know what that expression actually is, or what that polynomial is. Obviously, if there's a common factor in B and D, then you don't need to multiply them together. We can kind of simplify beforehand. Or if they're the same value, then obviously we can just put it there. So if you have x minus 1 over x plus 2 plus x plus 5 over x plus 3, then we're going to need a common denominator. Common denominator, we don't have any common factors in x plus 2 or x plus 3, so it's going to be the product of those. So we're going to have x plus 2 times x plus 3. And we're going to, this x minus 2 is going to get multiplied by x plus 3, so, sorry, x minus 1 will be multiplied by x plus 3. And then x plus 5 is going to get multiplied by x plus 2. X plus 5 multiplied by x plus 2. And we've done our multiplication. Now obviously with this, we can go further. And on this one, I'm going to go through that. I'm going to do that additional step there of actually going through this. Because you can't just leave it like this. Because this is not a rational expression as it is written right here. Because we have a product of 2 sums or differences added to another product of 2 sums or differences. So basically we have a polynomial plus a polynomial over, whereas we really should go through the work. So if we have x minus 1 times x plus 3, that's going to give us outer 3x, inner minus 1x. So that's going to give us 2x. First, x squared. Last, -3, minus 3. And then we've got x squared plus 5x plus 2x is plus 7x plus 10, 2 times 5. On the bottom, x squared plus 5x plus 6. And now we combine. So x squared plus x squared gives us 2x squared. 2x plus 7x gives us 9x. Minus 3 plus 10 gives us plus 7 over x squared plus 5x plus 6. Now realize at this point, there actually is the possibility that you might be able to simplify this, or actually I should say factor this, and come up with one of these. It can happen, so just be aware of that. In this case, two numbers that multiply into 14 and add to 9. Multiply 4, well that would be 2 and 7, right? 14 add to 9, which would break, so let's just verify that it doesn't do that to us. So we want multiplies to 14 and adds to 9. That's 2 and 7. So we have 2x squared plus 2x plus 7x plus 7 gives us 2x times x plus 1 plus 7 times x plus 1, giving us 2x plus 7 times x plus 1. And we see that it factored out nicely, but neither one of these is in the denominator. So we don't have to cancel any further. But it's a good thing to take note of there, that there is the possibility that you're going to come out with something that you can actually factor this and then simplify when you're adding or subtracting rational expressions. So I just wanted to go through that and show that process to you. And keep in mind that we're really just taking bits and pieces of everything that you've done in the past and pulling them in. We didn't really do anything new here. We just applied it differently. And in mathematics, that's really what most of it is. It's just different applications of the same things. Now, if you deal with subtraction, no real difference. A over B minus C over D is equal to AD minus BC over BD. It's really, the only thing that changed was we called that minus and we called that minus. You still need a common denominator, which is going to be the product of those two. You're still going to have to multiply this by that one and multiply this by that one, and we end up with the same thing. So I'm not going to show an example of that because it's really the exact same process. Now, sometimes we have to deal with finding a common denominator, the least common denominator. Here, obviously, and in the example that we just did, we found a common denominator. But let's take a look at, and we're not going to go through simplifying or anything else with it, but what if we have this? X plus 5 over 2x plus 6 plus x minus 7 over x plus 3. So we have the sum of two rational expressions. And our rule said multiply these two together to get the denominator, multiply this times that to get, and then multiply this times that to get your numerator. But notice that 2x plus 6 can be factored. If I factor that, I pull out a greatest common factor of 2 and I get 2 times x plus 3. Well, that means if I'm looking for a common denominator, I don't need to multiply this by x plus 3. X plus 3 is already there. All I need to do is multiply this second one times 2. So I just need to go times 2 times 2. So now I can say x plus 5 plus 2x minus 14. I just multiplied that 2 through while I brought it down, over 2x plus 6. So I guess I am going to go through it. So 2x plus x is 3x, plus 5 minus 14 is minus 9. We have 2x plus 6. So 3x minus 9 over 2x plus 6. And realize with this, and we can check and see, can we factor anything more out? If we factor out a 3, we get 3 times x minus 3. Here we get 2 times x plus 6. So there's nothing we can do to simplify this expression. Now, a final thing I want to mention about these rational expressions is just basically a rewriting of something we've already done, which is complex functions. So let me write that out since I'm not saying it clearly right now. Complex functions. Well, what's a complex function? Remember, we've related all this stuff to fractions. What's a complex fraction? Complex fraction, 3 halves over 4 fifths, right? That's a complex fraction. A complex function is the same thing. A over B over C over D. Which is just what? It's just division. AB divided by CD, which is just what? Multiplication, equal to AB multiplied by D over C. And of course, remember, you've got to make sure that you can't have 0 in a denominator, any part of this, is equal to AD times BC. So a complex function is just the division of two rational functions, and we have to follow all of the rules that we did when we're dealing with rational functions and when we're dealing with division of rational functions. So that's all it is, and if we were to simplify a complex function, all we would do is turn it into the division, turn it into the multiplication, and use the same processes that we have for simplifying a rational function.